Hello everyone. Chapter 5 covers numerical methods for differential equations or ordinary differential equations. So in section 5.1, we're going to learn the theory before we can do any numerical solutions to these things. So section 5.1 is basically all the theorems and definitions that you need for the rest of chapter 5. We will focus on linear differential equation of this type, and since this has an initial value, these are typically called initial value problems. So this is what we want to focus on section 5.1. So the first definition you need is this: a function f of ty, which is the right side of the differential equation, is said to satisfy the Lipschitz condition in the variable y. So it's very important that you understand there is the Lipschitz on the variable y on a specific set. So this is a subset of the r square if you have a constant L such that this is satisfied. Okay, so if the function evaluated y1 and y2 is less than or equals to the absolute value of y1 minus y2 times a constant, then it says that this function satisfies the Lipschitz condition, where these 2 points had to be inside the set D. Okay? And L is going to be called the Lipschitz constant for F. Again, just be aware that the Lipschitz condition is specifically for the variable y. Okay? All right, for example, let's look to this function. F of ty is equals to sine 2t minus 2ty over t squared. And the set where this is defined is the square where t goes from 1 to 2. So time goes from 1 to 2. And y goes from minus infinity to infinity. So it will be this rectangle. Okay. All right. So how much is then f of t y1 minus f of t y2? Okay, so this should be equals to sine of 2t minus 2t y1 over t squared minus sine of 2t minus 2t y2 divided by t squared. If you combine the like terms, you can see that these ones will cancel, and you will end up with minus 2t y1 plus 2t y2, everything divided by t squared. If you factor the t out, if you factor 1t here, it will cancel the exponent here. So this will give you minus 2y1 plus 2y2 divided by t. Alright, so then this implies that the absolute value of f of t y1 minus f of t y2 should equals to the absolute value of 2 over t times y2 minus y1. Okay, so how do we get that? Well, from here you can factor the 2y, the 2 over t, sorry, and this will give you y2 minus y1. It's just basic factorization. So then this is equals to the absolute value of 2 over t times y2 minus y1. Remember that the absolute value of a and b is equals to the absolute value A times the absolute value of B, and this is less than equals to 2 times y2 minus y1. Y is less than or equals to 2. Remember the t is between 1 and 2. So therefore that implies that 2 over t has to always be less than or equals to 2. So here you can see that this satisfies the Lifshitz condition. Okay, this one right here. And the value for the Lifshitz constant is 2. So this implies that L is equals to 2. Okay. So this is how you are going to check if a given function satisfies the Lifshitz condition on y. Alright? Okay, so let's move on to the next page. Let's look to the following definition. Set D, that is a subset of R squared, is called convex if whenever T1 and y1 and T1 and y2, so there is a typo here, there should be T1, y1 and T2, y2 are part of the set, then this order pair too, because all of this is technically x and this is y, they also belong to the set D for every lambda between 0 and 1. This is kind of tricky to see, so the best way to check if something is a set, a convex, to see if it is a convex set, is the following. Let's say that you have a set D that looks like this, so this will be D. Then you have another one that looks like this, okay, also D. Then you have the 2 points in here. Let's say this one is a T1, Y1, and this is a T2, Y2. If you make a straight line between the 2 points, you can see that the line, the full line, is still inside the set. So therefore this one will be convex. This is a convex set. On the other hand, they have a point here, the other point there, and again this is T1, Y1, this is T2, Y2. If you also make a straight line between the two, you can see that this part is not inside the set, so therefore this is not convex. The rest of the section and part of the chapter, we're assuming we have a convex set, and usually the set, it will be like a rectangle like this. Okay. Now let's look to theorem 5.3. Suppose that f of ty, remember that f of ty is technically just the differential equation, is defined on a convex set. So we have a convex set. If there is a constant L such that the partial derivative of f with respect to y is less than or equals to a constant for all ordered pairs, so for all t and y that are part of the convex set, then f satisfies the Lifshitz condition on D. This is the same condition we saw at the very beginning. So this term makes checking for the Lifshitz condition easier than the previous definition or the previous method, because all you have to do is take the partial derivative of f with respect to y, and if you can bound it, then it means that it satisfies the Lifshitz condition. Not only that, this will be the Lifshitz constant. For example, this is the same example we did at the beginning. So here what will be the partial derivative of f with respect to y? Well, this doesn't depend on y. This one doesn't depend on y. The only thing that depends on y is this part. So technically, then the partial derivative of f with respect to y is equal to negative 2 over t. Well, how do we get that? Remember, this is the same thing as minus 2y over t squared, which is negative 2 over ty. So you take the derivative with respect to y. This is the only thing you have left. Then you take the absolute value of this partial derivative. The absolute value of this is equals to 2 over t, which is always less than or equals to 2. We discussed that already. Why? Because the value for t is between 1 and 2. Actually, here you don't need the absolute value for this part, and this is always less than or equals to 2. And again, we already knew this. The value for the Lipschitz constant would be 2. As you can see, Theorem 5.3 may be an easier way to check if a specific differential equation satisfies the Lipschitz constant or condition on y. Now let's take a look at Theorem 5.4. Suppose that D is a convex set and f of t is continuous. If f satisfies the Lipschitz condition, which we talked about it twice already, on D, in the variable y, then the initial value problem has a unique solution. Okay? Now you will see in a little bit that the opposite is not true, but if f of t and y is continuous on the set, and if f satisfies the Lipschitz condition, then you can guarantee that this initial value problem has a unique solution between a and b for the time. Okay? You remember the previous problem we did, it was continuous between 1 and 2, and it satisfied the Lipschitz condition. So therefore, the previous example, which was y prime equals to sine 2t minus 2ty over t squared, will have a unique solution, assuming we have an initial condition, which we didn't have for the last part because we were only checking on the Lipschitz condition part. All right, but you have to be very careful with this. Look to this example. Here we have a convex. This is a convex set between 0 and 1. Or the set looks something like this. You have 0, you have 1. This keeps going forever for the value for y. If we use a Theorem 5.3, the partial derivative of f with respect to y is equals to minus e to the t times e to the minus y. However, as you will see right now, if you try the absolute value of this, can you really bound this? And the answer is no, because y goes to minus infinity. So therefore that means that f of ty doesn't or does not satisfy the Lipschitz condition. Okay, Lipschitz condition. However, this actually has a unique solution. For example, let's say that we add the initial condition of y0 is equals to 1. So you need to have that at some point. All right, so then this is what we have from here. We have the e to the y dy is the same thing as e to the t dt. If you integrate both sides, you end up with e to the y is equals to e to the t plus c. If we apply the initial condition of y0 equals to 1, so therefore that implies that e to the 1 is equals to e to the 0 plus c, which means that c is equals to e minus 1. So therefore from here we have e to the y is equals to e to the t plus e minus 1, or y is equals to ln of e to the t plus e minus 1. So you can see that this differential equation, or this initial value problem, has a solution even though it didn't satisfy the Lipschitz condition. So you can see that it's not an if and only if case. You still can have a unique solution even if the function doesn't satisfy the Lipschitz condition. Now, if it satisfies the Lipschitz condition, what the theorem is saying is that if you have a convex set, which we do, and if the function is continuous, which it is, and if it satisfies the Lipschitz conditions, then automatically you can say it has a unique solution. But if it doesn't satisfy the Lipschitz condition, it doesn't mean that it cannot have a unique solution. So you just have to be aware of that. All right, let's move on to the next. Let's talk about well-posed problems now. So an initial value problem like this one, initial value problem, is called well-posed if it has a unique solution, and we already have a way to check that. Also, to be a well-posed problem, you need to have a second differential equation or a second IVP, like this one, that also needs to have a unique solution. This one, this CDT, is called the perturb problem related to y prime, or to dy dt. Okay, so let's look to this perturb problem for a little bit. The perturb problem is a problem that assumes the possibility of error being introduced in the differential equation, which will be this part, and also in the initial conditions. This is very important because we solve this kind of problems in numerical analysis all the time. Usually, the perturb problems we do are related to round off errors. So that's what the focus of this problem right here. So what are these delta t and delta 0? Well, delta t is a continuous function that the absolute value has to be bounded by epsilon, where epsilon is any positive value, okay? And also delta 0 is bounded by that. Here we need to have a epsilon 0, which is positive, a k that is positive, and then for any epsilon where E0 is bigger than epsilon, then we have this condition that is satisfied. Okay. All right. The next theorem tells you how to check if a problem is well posed or not. So theorem 5.6 says the following. Suppose that you have a convex set. This is the same type of set we've been using the whole section. F of ty is continuous, and it satisfies the Lipschitz condition on D in the variable y. Then the initial value problem is well posed. So technically, all you need to have is a function that satisfies the Lipschitz condition on a convex set, and it will be well posed. Okay? So, for example, let's look to this case. Here you have f of ty is equals to 1 plus y divided by 1 plus t. You can check this is a convex set. So what is the partial derivative of f with respect to y? This will give you 1 over 1 plus t. The absolute value of this is clearly less than or equals to 1. So that implies that L is equals to 1. Alright, so remember from Theorem 5.3, that means that it has a unique solution and it satisfies the Lipschitz condition. So therefore, by Theorem 5.6, that implies the dy dt equals to 1 plus y, where 1 plus t is a well-posed problem. Okay, let's look to this example, which we looked at it before. Recall from the last time we saw this example, the f of t y didn't. Okay, so this didn't satisfy the Lipschitz condition. So therefore, this cannot be well posed. So that's easy. All right, let's try one more example. Consider the following differential equation. Here we have the f of ty is just equals to 1 minus y. You should check that this clearly satisfies the Lipschitz condition, which is very, very easy to check. Now, how do you solve these differential equations? Well, there are two methods to do this. You can either use separation of variables, or you can use the integrating factor. So let's do the separation of variables. Remember that y prime is just dy dt. So you separate the variables, you end up with dy over 1 minus y is equals to dt, which implies minus ln of 1 minus y is equals to t plus c, which implies that if you apply the initial condition y is 0 equals to 0, you're going to end up with minus ln of 1 minus 0 equals to 0 plus c, which implies z is equals to 0. So therefore we end up with ln of 1 minus y is equals to minus t, or e to the minus t is equals to 1 minus y, or y is equals to 1 minus e minus t. So you can see this has a unique solution because it satisfies the Lipschitz condition. The question is this a well-posed problem? All right, well, consider delta t to be of this form. So let's say that delta t is given in this specific form, where delta here, this is a constant. So it's just a constant times t. All right, so then we're gonna get the following perturbed problem to look like this. So we have let's say dz dt is equals to 1 minus z plus delta t, but delta t is just delta times t. And the initial condition is going to be z of 0 is 0 plus delta 0. Remember that all of this comes from the original initial value problem, which was this 1 minus y, and y of 0 was equals to 0. Okay? And this is the associated perturb problem with this one. All right, so then how can we solve this problem? Well, we're gonna have to use now the integrating factor method, which everybody should have seen at some point in your life. So therefore, this is what we have. You can rewrite this as dc dt plus z is equals to 1 plus delta t. So then the integrating factor is going to be e to the integral of dt, which will give you e to the t. Recall that for the integrating factor, in case you forget that already, the equation usually looks like this: y prime plus p x y is equals to qx, and then the integrating factor will be e to the px dx, or this could be a value of function of t, which is our case. So in our case, the value in front of y is 1, so therefore the integrating factor is going to be e to the 1 times dt, which is just e to the t. Then, remember, once you find the integrating factor, you need to multiply both sides by e to the t, which will give you e to the t dc dt plus e to the t c equals to e to the t plus delta t e to the t. Remember, the whole point of using the integrating factor is that you can rewrite this as just e to the t z prime, and the other side is just e to the t plus delta t e to the t. Then you integrate both sides, and on the left side we end up with just e to the t c, because the integral cancels with the derivative. That's the whole point of the integrating factor method. And in the other side, when you integrate this with respect to t, the integral e to the t is just e to the t. Remember that delta is just a constant. You need to use integration by parts to integrate this. And if you do integration by parts, you end up with t e to the t minus e to the t plus another constant. Remember, this is integration by parts. You should check this. This is all from calculus 1. Now remember that the initial condition says that z of 0 is equals to 0 plus delta 0, which means it's just equals to delta 0. So if we plug it into the equation, that means the delta 0 e to the 0 should be equals to e to the 0 plus delta times 0 minus 1 plus some constant. Well, recall that anything to the 0 power is 1, so therefore we have delta 0 times 1 is equals to 1 plus delta times negative 1 plus c. So that implies that c is equals to delta 0 minus 1 plus delta. You should check this. So therefore the solution to the differential equation, z is equals to 1 plus delta times t minus 1 plus delta 0 minus 1 plus delta e to the minus t. How do we get that? Well, remember that here you had to divide, once you figure out the value for the constant, you need to divide by e to the t in both sides. So you divide by e to the t, this will become a 1. This one also becomes a 1. This one will be a 1, this will be a 1, and this will be e to the minus t on this side. The value for z was equals to all of this. So that's how we get this. And then you combine these two, you end up with this part. Alright, so the last part we had to check is this. Okay, the last part we check is if the distance between z of t and y of t is less than a constant times epsilon. So therefore, if we do z of t minus y of t, you should check that you end up with something that is less than or equals to 2, the absolute value of delta plus the absolute value of E0. So you should definitely check this. It's basic algebra. And this is less than 3 epsilon. So therefore that implies that the value for k is equals to 3. And that's it for 5.1.